These fish eggs are really tiny. They're almost microscopic. We can inject hundreds and hundreds of eggs in the span of a couple of hours. These are some eggs that have just been collected, some small fish. You can see them swimming around, how tiny they are. My name's Jason Berman, and I'm a pediatric oncologist and a clinician scientist here at the IWK. We use a fairly innovative model system, the zebrafish, which is a common tropical fish you can find at your local pet shop, to study blood development and cancer, specifically leukemia. What's remarkable about these little fish is that they actually have very similar blood development to humans. Not only do they have the same types of blood cells, but the genetic programming that determines how those cells develop is very well conserved down to zebrafish. And because leukemia is a disease of disordered blood development, that allows us to be able to study that in the zebrafish model. We have about 10 people in the lab, and that ranges from postdoctoral fellows to technicians, undergraduate students, and even some high school volunteers. So people at all different levels who've come into the lab to help make a contribution. The advantage of the zebrafish is that they reproduce externally. They're not in the womb, and they produce many, many embryos. Those embryos are transparent and grow up externally, so we're able to look at them and track their blood cells and their blood development very easy just looking under the microscope. Remarkably, their blood is very similar to humans. Things that we do in the fish have a direct impact on humans. We are studying a rare type of leukemia called acute myeloid leukemia, and a special aggressive subtype of that leukemia. And through creating a fish model, we've learned about how that leukemia affects blood cells, keeps those blood cells dividing and not responding to stress the way that they should be. So that's been helpful, and that may give us clues as to better ways to treat that type of leukemia. We know that in leukemia, it's not just the leukemia cells, but the other cells in the environment that also contribute to making that disease aggressive. We've been studying one of those types of inflammatory cells in the fish called mast cells, which are the first players in that whole process, and we were the first group to identify those cells in the fish and allow us to be able to study how those cells contribute to cancer using the fish model. Most recently, we have been working on actually taking human leukemia cells and transplanting them into the fish, something called xenotransplantation, which will allow us to study how the leukemia develops in the fish and allow us to actually treat those fish with different drugs and see how those human leukemias respond. We need to have these animal models to go from studies that are done in a petri dish before we take them into trials with humans. Currently, most of the treatments that we use, most of the chemotherapies, are actually fairly non-specific. They basically target cells that are dividing all the time, but they don't actually go after the specific abnormality causing that cancer. We believe that in leukemia that there's probably a few small cells, these so-called leukemia stem cells or initiating cells, that actually are the cells that have caused the leukemia, and those are actually not affected by the chemotherapy. So whereas you may get someone in remission, after a period of time those cells start the process of dividing again. But if we are able to learn more about what those genetic abnormalities in the leukemia cell are, then we may be able to design specific therapies and identify specific therapies that really get to the heart of the matter and target those abnormalities. Through the use of multi-agent chemotherapy and clinical trials through groups like the Children's Oncology Group, which we're active members of here, we've really made huge strides both in terms of the cure rates in these diseases, but also in terms of lessening some of the side effects. But we're not there yet. So through using the zebrafish in our lab, we're working on trying to develop better treatment approaches that specifically target the abnormalities that cause this leukemia, so we'll have even higher cure rates with less side effects. One of the advantages that I have in the type of research that I do is not only am I a scientist, but I'm a clinician as well. So when I'm not in the lab doing research, I'm looking after patients upstairs on the oncology floor that have leukemia, that have cancer. And so the questions that we ask in the lab, the scientific questions we ask, are directly linked to things that I'm seeing in my patients. I have patients that aren't cured despite whatever efforts we make with multi-agent chemotherapy, sometimes even a bone marrow transplant. And so I get the opportunity to see firsthand how the research we're doing in the lab can make an impact on improving the outcome for the lives of my patients. And a lot of them are quite interested, and I'll bring them and their parents or their families down to the lab, and usually they're fascinated that, particularly if we're studying a disease that they're living with, we can show them, here's a fish that has the same type of disease that you do that we're studying to try and come up with better treatments. We keep finding at the molecular level the same pathways seem to be involved in many, many types of cancer, and so the more we learn about those pathways and how we can interrupt the signaling in those pathways at a molecular level, I think those will have an impact on many types of cancer. The current genetic era, or really the genomic era, we are learning more and more about cancer and how cancer develops at a rapid rate. We're learning a ton, and we'll be able to apply that information to develop new treatments in the future. We're now poised to actually start testing some new drugs, trying to identify sort of new drugs in some of these model systems, so I think the next few years are going to prove to be very exciting in the lab.
Please support the IWK Radiothon on C100. 1-800-595-2266 or C100FM.com.